So I've set up a little challenge. We're going to have infection given exposure of a susceptible. It's going to be probabilistic. It's going to depend on a transmission probability. I want it to be more intention revealing yet for communicable disease folk, infectious disease researchers. I could say transmission probability per discordant contact. But we'll strike a balance here. I'm going to add in a parameter, transmission probability. Oh, it's being truculent in its normal silly way here for me. I don't know what's possessed it today. Okay. Yeah. Okay. Transmission probability. And its default value will be 10% per exposure. This is the beta, for those familiar with the mathematical epidemiology. Per discordant contact, there's a certain chance beta of transmission. Sometimes beta is used for a broader set of constructs of beta times C, but I'm using specifically here as the per discordant contact chance of transmission. There we go. And now we have to actualize it. That's a nice idea, but let's make it so. And then we're going to have to do some bit of fancy footwork for reasons that you'll see. These standard patterns. Once you've seen this before, you kind of get wise to it, and you know the mistakes. Just like an old grizzled MIT professor told me one time. He said, "Nate, when we get older, we don't get any wiser, but you become a lot more sly." And someone else chimed in, another older professor, and said, "Yeah, it's you see the students make the same mistakes again and again, generation after generation. You can just smell where they're going off the road, and you can guide them back. Same patterns recur, some characteristic failure modes, same characteristic dangers. You become more sly. You know the dangers. You know where great is the enemy of good, and you head that off, etc. Okay, so nominally, what we want to do should be pretty easy. We go and we use a branch. I've seen these things before. And by default, excuse me, if a condition is true, they'll get infected. That'll be the condition. This will be transmission. This one, by contrast, will be called not infection, will be called exposure. Okay, exposure. It's not necessarily transmission. It exposes someone. If they're in a susceptible state and they've been exposed, they will have a certain probability of getting infected. This one is called transmission. And the condition will be, it's going to be a coin flip. Bernoulli trial. Random true. Yes, we'd have another causal pathway. And in fact, that's where we're going. That's where we need to go to deal with pathology. You'll see demonstrated in a minute. But yes, that's right. That's right. We'd have another pathway. And conceptually, it's a different generative pathway. It's a different thing. And we might want to keep track of we might want to keep track here, for example, of the different number of infections that have occurred via each different pathway, right? Maybe log them, report that one occurred. Might want to eliminate one or turn one off when we don't turn the other off to understand the relative effect of environmental transmission versus animal to animal transmission. Maybe transmission through manure versus nose to nose contact, for example. So we're going to have for this, they'll actually get, in fact, I'll answer Jeff's question in a second. Oh, no. It's going to be transmission probability. Hey, oh, what am I doing this? I'm doing this. Muddling around when I'm too tired. Okay. Transmission probability. That's what we want. Okay. And make sure it builds. Make sure it's happy. Okay. Now, Jeff asked a question. Could you do the same with this thing called a guard on the transition? And the answer is a negatory. So the guard is computed at the time that you come in. It basically determines, is this, for your time in this state, your entire time in that state, is this pathway out disabled or enabled? If the guard is negative, you ain't going this pathway during that stay in this state. And so if a message comes in, you'll blithely ignore it if it's disabled. If your guard is negative, it won't do it, and it won't be reevaluating every time. No, it'll do it once when you come in. So guards are useful, but they're to be used fully conscious of their meaning. Their meaning is when you come into that state, it will determine, is that way out eligible for this stay in the state? And that's very different than like every time if infection occurs, I roll a dice for that. In the effective states transition, yeah. You mean sorry, like the infective? You mean like this guy's transition? This one, like the contact transition? Yes. Oh, that's no, I think because you don't leave the state when this fires, you're not going to be re-examining the guard. If you left the state and came back in, if it was like a loop out, then yeah, it would re-examine the guard every time. But generally speaking, you want to stay in this state because you might have things you want to record when they're entering this state, etc. And you want to be cautious about too many things that leave this state and come back in. We do that. We do that particularly to recalculate hazard rates, but not. I don't. I think it's too dangerous. I wouldn't do it. Okay. Okay, and this we should give a name, which is exposure without transmission. That's what this little one is. What's this guy? One's called exposure. Make sure that that's properly labeled. Make sure this one has a name, a face upon the world worthy of it. Transmission. Maybe we'll put it over here. Transmission. Make elements of the model intention revealing. It'll help you find problems. It'll help others find problems. It'll help foster that learning that lies at the heart of modeling. Okay, so here we go. Now, this is a nice little design. But it's terribly fragile. Why do I say that? Well, there's a count initially infective that's 5. That's what it says. It says count initially infective. But the action belies that because count initially infective in the initial infective event is sending, you might recall, exposed messages to these 5 susceptible people, 5 distinct susceptible people. That will lead them to here, but chances are they'll never get infected. We'll be lucky if one of those 5 become infected, much less all 5 is intended. So this is a issue with this initial sending people a message. Now it's easily dealt with, and it's dealt with in the manner that yes, the branch can be used to log attempted transmission. I would note you're sending these to me with direct message. So Jeff, so you might so the way is to apply Sarah's method. Sarah's. So here we want to add another transition, another pathway that's a little bit of admittedly an artificial construct. It's a little bit artifactual. And I apologize for it, but I've seen worse, believe me. And so has Wade. Okay, so what this one is going to be called, forgive me, force infection. Hey, force infection. It's going to be a message transition. And this is being truculent in rather distressing ways. On a particular message type, and goodness. And the message is going to be force infection message with a capital. Java distinguishes between things with lowercase and uppercase, so this won't clash. Force infection, I'll say message, just so it's clear. But I got to go put that in my list of messages. And that will mean if I force the infection, that'll be a straight shot. It won't mess around. It won't horse around, as my dad would have said. Okay. So go to the project, go to the message type, put it in here, force infection message. We're almost done, except that initial infection event needs to send force infection messages, not exposed messages. As they say in China, the old horse knows the way. You've seen this again and again and again. This is, I don't know, 50 times or something. Okay. Force infection message. So what we want to do is in main, the initial infection event, we want it to send force infection message. Don't worry, I'll rehearse what I just did. I know it went kind of fast. Okay, so what did I do? I noted that, look, the problem with this scheme by itself, without this force infection message, problem with this scheme is that we have to infect a certain number of people at the start. And the way we're doing this, sending messages. And that all worked as long as those messages definitely infected people. because the intention was to start with 5, in this case, certain number of infective people. And if we had a surefire way of turning them infective by sending a message, that's what we were doing. And that's what we had. But now we've changed it to probabilistic. And that's all well and good for what we're capturing about the world. But now that initial infection event where we say we want, let's say, 5 infectives, it's going to send messages, and a lot of them won't even get infected. Quite possibly none of them will get infected. So if each has like a 10% chance of infecting someone. So we need a surefire way of doing it. And one thing we could do is put in a different pathway called force infection. That's what we did. We called it force infection with a lowercase f on the particular message called force infection message, a capital F. And we had to define that one, force infection message, in the option list. These are the type of message. And then finally, to complete the thought, I call it force infection message, but yeah. The reason I did that is because there was also this force infection transition, but it was lowercase, and so it wouldn't clash. Yeah. Anyway, initial infection event here needs to send a force infection message, not an exposed message. And after that, Bob's your uncle. It's going to work. Thank you, Jeff. That's great. Okay. Okay. So now we can force infection. By the way, that's a reason accrued to using initial fraction of the population starting and dividing people up between these from when they come into the state chart. That avoids this issue of needing to like send a message to make them infected and message was get ignored or whatever. You can just divide people up, start them here. You start them in that state of infectives, just like Athena was full born from Zeus's head, fully aged, as an adult. They come into the world in the infected stats, like Athena striding out of Zeus's head, for those who know Greek mythology. Okay, here we go. Okay. So now we have some people starting effective and some people, so there we go. Here we have 18%. It's still spreading pretty quick. 10% chance of infection given exposure, but we have a meteoric rise. And it's not yet 3 days in, so people are not yet recovering. But now we're starting to see, I think, there's going to be some recovery starting to go on. Okay, and there we go. Yeah. And then it kind of peters out. Okay. Okay. Now there's going to be a certain set of parameters for which the induced dynamics will be quite different, where it will stay. The structure here admits, remember, the structure determines possible modes of behavior. Parameters will generally set which set of modes are exercised in a given model. Sometimes stochastic shape. Well, your chance. There's going to be certain parameters. Is a new force of infection. This new force is independent of contact. It's actually not force of infection. It's force infection. It just right. It's like we're saying basically, hey, you're nominated. You're going to be the patient 0 or patient 0, 1, 2, 3, 4. Like we just require someone, you start infective. And so it's independent of contact. It's just boom, you're infected. That's one way to do it. And this is one of the awkward things. You got to kind of put that in. And then a stakeholder will look at that and say, what's that? Is that like, vertical transmission? And you say, no. So, no, it's just because we have to start people infective and we can't have every probabilistic. It's one of the problems with this, that it gets in the way of stakeholder understanding. And dividing people up, when we have a very probabilistic thing, I tend to prefer to kind of divide people up. But then you're not going to be having a certain number generally go, although there are ways to engineer that too. Okay. Yeah, there are ways to. Okay, I'm going to go add another, just to sort of, I'm going to say half halved transmission rate. Oh, no, wait a minute. I already have that here, but but this is half expect. Yeah, so I'm going to say halved baseline transmission rate. Yeah. So I'm going to lower it 0.05. Yeah. And I want to see like what comes about. So the big picture here is, people are circulating into these different spaces. So this one didn't even catch at all. Looks like it died out. I'm going to set it to random number seed here for it. I'm going to properties random number seed. But it looks like that particular time, it just petered out. Which kind of can happen. Here we go. And now people are starting to recover, so it's not going to probably peak nearly as high a value. And once again, it's dying out. It's just not enough people waning immunity by the time that it's circulating in their environs again. Maybe I'll do a half waning immunity time. Let's try that. I'm really curious what induces halved waning immunity duration. So waning immunity duration here is 1 per month. I'll make it 0.5 per month. So, excuse me, that's a rate. So it's going to be 2.0 per month, 1 every half months. So it's only going to be 2 weeks. Maybe I'll do it, once per 2 weeks. That might be an easier way to think about it. 1.0 divided by 2.0 times week. Once every 2 weeks. That's the rate. The mean time stay infected, stay immune is 2 weeks. Watch that. Okay, build. Make sure it's a happy camper, and we're going to run it. And here we go. Oh my God. Yeah. Yeah, you could see it's, oh my gosh, there it's coming back. Second wave, not as high. This one only went up to about a third of the population, not like 90%. Now we're in the third wave. Smaller yet. It could, by chance, undergo a die out again, but thus far it's hanging on by its claws. There it goes again, another wave. Okay. So it's spreading among these venues, affecting people probabilistically. Parents bring it home to their families. At a home, kids can bring an illness from home to their schools, can spread to other families from their schools, and the cycle continues. Notice the bottom of this is not at 0. It's pretty significant. It's circulating at a rate that doesn't go down to 0. You'll notice that there are these cycles in it, and in general, it's going to induce some quasi, not fully periodic, but there's going to be certain statistical patterns in the periodicity of this that are not going to be random. Another outbreak rarely starts just after another because it's depleted susceptible. So this induces certain, it's actually what we call a lower dimensional space than you might think. It's circulating at what's called on some lower dimensional manifold. It's not exercising all possible trajectories up and down. No, it's just a very small set, and certain patterns are induced by this complex interaction of people that have a lot of structure to them dynamically. And if we were to look at something like an autocorrelation function here, you'd find that each outbreak terribly, it'll be anti-correlated with an outbreak coming right after it. But if you were to look at periodicity and outbreaks, you would find some defined, some probably defined modes that would, periodic modes that would tend to be dominant at a certain frequency, just like in older years, pre-vaccination, you would have periodicity in pertussis, or periodicity in outbreaks, or periodicity in measles outbreaks. Okay. Enough said, enough musing. This is our neighborhood mobility model in an abstract space. I will post, and we will take a 5-minute break. And after that, resume, and I think take this thing into a geographic context as time allows. Okay, back in 5. Thanks.